Hi, I'm Saish and I'm here with my colleague Nitin, and together we're going to talk about WhatsApp's relay infrastructure. So, I've been an engineer at WhatsApp for about 5 years now, and I'm really passionate about building networking products that truly scale. So, I'm going to let Nitin initially kick off the talk and set some context about WhatsApp calling, and I'll jump back in later and talk about some really interesting technical challenges.
I'm Nitin, an engineering director at WhatsApp. Previously, I was a distinguished engineer building consumer products like Google Assistant and YouTube Search. And now let's dive in. At WhatsApp, our mission is to connect the world privately. And we want to provide a place where the most meaningful conversations in your daily life can happen. Our lives are increasingly becoming digital, and COVID has accelerated that. Our users want ways of connecting with each other in a more meaningful way. That is to share the moments together and get more done, whether it is through one on one or a large group setting. Users have adopted WhatsApp in more than 190 countries, making well over a billion calls daily and over a billion hours of call talk time on a weekly basis. And this massive scale creates unique challenges in scaling the system. At WhatsApp, we want to protect what is important to our users. So, one thing that resonates universally is our commitment to keep conversations private and safe. We always design our services in a way that protects people's communications. We are among the first apps to enforce end to end encryption for all forms of communication, including calling. We believe in refining functionality till it works for everyone. Rather than provide hundreds of features, we focus on providing a simpler, non cluttered experience, which is focused on perfecting the most important details that matter to our users. Everything from user interfaces to the backend architecture follows the same set of principles. So, we want to ensure that anyone can make a WhatsApp call on any device or on any network. It really matters that I'm able to reach my dad, for example, on any device, even when he's on a poor network. And especially it is an international call. So we want our call to be functional even on a high speed connections on the latest set of devices, or whether it is on a flaky network on low end devices. And that is what we mean by reliability for everyone. Now, I hand it over to my colleague Saish, who is going to talk about the relay infrastructure.
Thank you, Nitin. All right, so let us look at what a calling relay is. So, the process of setting up a call initially happens via the signaling server. Once the call is set up, the relay server steps in, and now it is responsible for shuttling the audio and video packets back and forth between user phones. The relay service is an essential part of maintaining the connection and is involved throughout the duration of the call. The relay architecture must continuously evolve to keep up with the ever increasing demands for scale and capacity. Calling products enable us to feel connected with our friends and family. And so users have very high expectations of them. We will pick four very specific user expectations or user needs and see how they map to technical challenges. And then we'll see how we solve them at WhatsApp. So the first user need is the ability to feel present with the people that we're having a conversation with. And it doesn't matter whether they're across the street or halfway across the world. The best calls are where the conversation just flows smoothly and naturally, just like it would in person. This is our ultimate goal with every call. So, what are the technical challenges here? So, the things that affect the feeling of presence are network latency and packet loss. Network latency introduces lag in conversations and interferes with the natural flow of conversation. Packet loss creates issues like video freezes. So, how do we deal with these issues? Meta has powerful data centers which we can use to relay calls. But due to the scale of these data centers, there are very few of them and they are pretty far from the end users. Instead, what we do is we run the relay server on thousands of Meta points of presence, or POP in short. These thousands of POPs were initially built for Meta to support the content delivery network. Running the relay service on the POPs brings the calling relays much closer to the end users and helps reduce latency. During the initial call setup, we use sophisticated targeting algorithms to pick up the most optimal cluster for a particular call, and this helps minimize latency. Things can change during the call. For example, you might switch from Wi Fi to cellular, and at every change, we need to reevaluate which is the most optimal cluster for the call and make a change if it is necessary. Despite being close to the end users, packets traverse multiple networks to get to the relay server, and packet loss is often an issue. To deal with packet loss, we have two strategies. One is preventive and one is reactive. The preventive strategy revolves around preventing congestion. The top cause of packet loss in networks is because of network congestion. So, how do we prevent network congestion? So, the best way to do this is by accurately determining bandwidth estimates for a connection and then to limit bitrate so that it prevents congestion. But some networks will have packet loss regardless. So, how do we deal with that case? So, in this case, what we do is we cache media packets on the relay server and retransmit them if we detect that any packets are dropped. So, in summary, we use a global network of relay clusters and targeting algorithms to reduce latency. And the relay servers use sophisticated algorithms to estimate bandwidth accurately to prevent congestion and employ techniques like caching and retransmission to reduce packet loss. So, let's move on to the next user need. Users want to minimize battery usage as well as data usage. Data plans in some regions continue to be expensive, and we cannot even assume that Wi-Fi plans are unlimited for everyone. So, what are the technical challenges that this poses? Encoding and decoding, encryption and decryption, these are all CPU intensive operations. More CPU usage means lower battery life. More video and audio streams, especially in larger group calls, means higher bandwidth usage. Let's consider this example of a 5% group call. All users are transmitting audio and video streams. If the relay server forwards all the streams, then each participant would get 4 incoming audio and 4 incoming video streams. More streams means more bandwidth usage. And it also means more CPU to decrypt and decode these streams, lowering battery life. All calls at WhatsApp are end-to-end encrypted. That means the relay server does not have access to the contents of the stream, so it cannot mix the incoming streams into a single outgoing stream. So how do we solve this? We use a process called selective forwarding. This is where the server intelligently forwards only some of the streams that it receives. Let's see an example of this solution using an audio call. As you might expect in an audio call, not everyone is speaking at the same time. There is usually just 1 or 2 people speaking at any given moment. So we could transmit audio just for the people who are speaking, and this process is called dominant speaker detection. Because of end-to-end encryption, the relay server cannot directly access audio contents in the media. So how do we know who is speaking in the call? To figure out who is speaking in the call, what the relay server does is it accesses volume information from the device itself. By accessing only volume and not the contents of the audio, the relay server preserves the privacy of the call while getting just enough information to make a forwarding decision. So in summary, we conserve device resources by intelligently limiting the number of streams that we forward to users. Dominant speaker detection is a great example of this. Now let's move on to the third user need. Users want to have the most optimal call quality and experience possible that their device and network allows for. The biggest challenge we face here is not on the variety of networks, but the asymmetry of network conditions on a single call. In a single call, some participants could have fantastic network quality, while others could have poor quality. Because of end-to-end encryption, the relay server cannot downscale video to suit the users of poor networks. Let's see how this happens in a real video call. Here's an example of a 5% video call where one person is on a bad network. If we transmit a high bitrate stream, everyone on the call gets great quality except for that one user. That one user has a particularly bad experience because the high bitrate causes excessive congestion in their network. What if we send low bitrate streams? Now the users on the poor network would be able to participate in the conversation, but everyone else on the call, despite their great networks, would have a poor experience. So how do we solve this? What we do is the relay server tries to detect that there are multiple network varieties in the call, and if it detects this case, it pulls both high bitrate and low bitrate streams from the devices. The relay server then intelligently forwards the high bitrate streams to the users on the good networks and forwards the low bitrate streams to the users on the poor networks. This method is called video simulcast, and it allows everyone in the call to have an optimal experience while still preserving end to end encryption. To summarize, the relay server adapts to individual user networks and provides them the most optimal call quality possible based on their network. We use techniques like video simulcast while preserving, so we can preserve end to end encryption. Now I'll hand it over to Nitin to talk about the fourth user need.
Now, let's talk about the most important aspect of calling, that is reliability. One aspect of reliability is drop calls, because nothing is more frustrating than a call dropping midway through an important conversation. We should not be dropping calls during maintenance events like the software upgrades or cluster resizing when we are load balancing between the servers. We don't want the calling service to be unavailable even during the extreme situations. So our architecture should guard against catastrophic failures in times of extreme load. So we discussed how the relay service runs on thousands of POP clusters worldwide. Now let's zoom into a cluster. Each cluster contains hundreds of containers of the relay service. Connections are load balanced onto the cluster, and every participant in a call can end up in a different container, fairly distributing the load across the entire cluster, irrespective of the group size or the duration of the calls. So containers can go down during the planned events like the upgrades or during the cluster resizes. So what happens when a container that is handling the call goes down? So we try to load balance by detecting it and simply redistributing the traffic among the remaining containers. When a container picks up a connection from another, it needs to retrieve the call state from the old container so that it is able to continue relaying that connection. For this, we have a state server where we can save the state, and there are essentially two different types. Call states like the group size and the network addresses are critical, so they're always persisted to the state server. State like bandwidth estimation and who is speaking in the call constantly changes, so and does not need to be persisted like the persistent state. By being selective about what kind of state to persist, we improve the reliability without actually compromising on the scalability. There are several cases where calling can be under extreme load because a lot of people are trying to make a call at the same time. Every New Year's Eve, I get a call from my dad, just like many other people all around the world. Exactly at the stroke of midnight in every country, you see a huge spike in the calling volume for that region. It's similar when there might be a natural disaster or the world events where people are trying to reach their loved ones. As long as the internet is available, we want calling to be possible. Our systems are designed to handle these spikes and avoid catastrophic failures. As call volumes increases, resources like CPU, memory are automatically monitored, and throttling kicks in as we approach predefined limits. We have clearly defined priorities that can help us decide which calls are more important in case the capacity runs out. For example, ongoing calls are more important than the new calls. A system throttle the setup of new calls to allow the infrastructure to maintain the quality of the ongoing conversations. Similarly, one-on-one calls have a prioritization over the group calls. So to summarize, the relay service are designed to function even with the partial component failures. When faced with extreme load, the relay service is designed to gracefully degrade and to prevent the cascading set of failures. Relay infrastructure plays a critical role in the WhatsApp calling experience. Using end-to-end encryption, we ensure messages and calls stay private, and no one else can read or listen to them, not even WhatsApp. Our media relay solutions uses novel approaches, like filtering the non-critical audio streams or delivering optimal video quality even when participants join a group call with a varying set of network characteristics. By keeping our experience simple, and the solutions performant. We continue to connect people through calls of different sizes, on different devices, and on different network conditions. We constantly raise the bar on reliability, so we preserve the continuity of ongoing calls, even when individual tech components might experience failures. The solution scales to more than a billion calls daily, but it also handles predictable spikes during the New Year's Eve or unpredictable but critical moments like the natural disasters. Behind every product decision and the tech innovation is a desire to help people communicate anywhere in the world without barriers.